Hi students, in this second video for online lecture 16 and chapter 9, we are now going to talk about electrolytes and the precipitation reaction. So first thing we need to talk about are the components of a solution. A solution is a homogeneous mixture of two or more substances. The first part we want to talk about is what we put into solution, and that is the solute. These are the substances present in the smaller amounts. Historically, these are either solids, but they can also be liquids or in some case gases. The solvent is a substance present in larger amounts. For a majority of the substances and mixtures that we see in this chapter, we are going to have our water be the solvent, so we're going to call this an aqueous solution. So let's look at a few examples. If we think about soft drinks, well, let's talk about a Texas staple, and that is going to be Dr. Pepper. What is the solvent in our Dr. Pepper? Well, if you look at the ingredients, you'll see that it says carbonated water. So water is actually the greatest abundant species in our Dr. Pepper. So what solutes do we have in there? Well, we have a multitude of them. Not only do we have our CO2, we have sugar, we have dyes, and there's caffeine. So as you see a soft drink being a homogeneous mixture, it contains many solutes in a predominantly water solvent. That is a solution. But everybody thinks that a solution can only be a liquid. Can I have a gaseous mixture? Let's talk about air. Air, we breathe, actually is a mixture of many gases. Do you know what is the most abundant gas in our air? At about 78%, it is nitrogen, not the oxygen that is keeping us alive. Our solutes in our air are the oxygen that keeps us alive, argon, methane, and other trace gases. It is also true that we can have solid mixtures and solid solutions. Solder is what we use to help build electric conductivity in electronics. Originally, back in the old days, the solvent was lead, but due to its toxicity, many companies are now producing lead-free solder. While the solute has not changed, and that is going to be tin, and that's what helps with our electrical conductivity. The solutions you're used to normally seeing, however, are going to be your laboratory solutions. So here you see that we have aqueous solutions of potassium permanganate, and you can see which ones are more concentrated of the two because it has a more vibrant purple color than instead of the faint purple color that is associated with our permanganate. So our solutions are going to be ever critical as we start to go through this chapter. So as we look at a solution, we need to see how it behaves. We like to have solutes that dissolve. That means to go from being a standalone solute to being part of a solution. But we now have to bring in a more important word, and that is dissociate. If something dissociates, it is going to be an electrolyte. An electrolyte is a substance that, when dissolved in water, results in a solution that conducts electricity. A non-electrolyte is a substance that dissolves, but doesn't dissociate, doesn't break up, and therefore does not conduct electricity. So here you can see what a non-electrolyte looks like and behaves. Here is what you think is a clear colorless solution, but it actually has a solute in it. But if we pass an electrical current through it, it doesn't complete the circuit because it doesn't have ions to pass that electricity. Then we have weak electrolytes. This means that they dissociate part of the time, so now we're going to have some ions in solution. As you can see, we are going to get a faint light instead of no light or a bright light. A strong electrolyte is going to give us full electric conductivity, and you can see here that even though I have a clear and colorless solution, we have plenty of ions in solution, completing our circuit and allowing the electricity to flow. So now that we've seen how this behaves, what does this mean on a microscopic level, so that way we can look at the behavior of our molecules? So let's think about what we need to go and conduct that chemical train. Well, if we want electricity, our best thing to have is a cation, meow, and an anion. This means that we want to have our ionic compounds. So a strong electrolyte dissociates completely. This means that if we put it into solution, it would prefer to be the ions and not the solid. An example of this is sodium chloride. We also have other examples of that, and that is potassium bromide as well as sodium nitrate. Notice that when I put them in water, they will dissociate into their stable ions that we predict as either the polyatomics, our alkali metal cations, meow, or our halogen anions. So their stability allows them to sit in solution, and this means that we then have the ability to conduct electricity. Weak electrolytes, however, do not completely dissociate. As you can see here with this acetic acid, you will notice that it will dissociate into the acetate anion and an H+, but as you can now see here, there is a double-headed arrow. This means that our products can go back and form the reactants due to their electronic instability. The acetate ion isn't all that stable in solution and would prefer to go back to the acid form. Another example of this is HCN. This, when put into solution, forms our cyanide anion in H+, but it does in a small amount and would prefer to be as the HCN in solution. This is what we call a reversible reaction. This means that the reaction can occur in both directions. We have seen reactions up to this point that would prefer the forward direction going towards completion of the products, but now you are going to see reactions in which we have a fighting going backwards and we would like to reform the reactants. For the most part, in this chapter and in Chem 119, we will deal with the strong electrolytes. But the weak electrolytes are coming, as that we are going to talk about them in equilibrium in Chem 120. So as we said here, acetic acid and our hydrocyanic acid are weak electrolytes. They don't ionize completely. For our acetic acid, normally we will get about 1 to dissociate out of about every 10,000. When it comes to the hydrocyanic, it's about 1 in a billion. So now you can see how important it is that we know those ratios, and you'll be taught that later. For this course, we like the strong electrolytes because 100% dissociation is very easy to predict. But the question becomes, how do I know how to predict those? And that is going to be the solubility rules that you see later in this video. So finally, what happens if we have no cations, meow, or anions in solution? Well, these are going to be your non-electrolytes. You see an example here when it comes to glucose. C6H12O6, when put in water, will dissolve, but it does not dissociate. It stays intact. Another example of this is methanol. Your low molecular weight alcohols are really miscible, meaning dissolves in water, but they don't dissociate. It stays intact. So how can we predict these, and how can you start to understand as we are starting to go through? Well, let's first look at the strong electrolytes. As you see with this group here on the left and at the top, these are going to become your strong acids. You are going to see these in great detail as we go along. The nice part about the strong acids are once you know them, if it's an acid and it's not one of those groups, then we will consider it a weak acid. Weak acids are going to fall in under the weak electrolytes. So our strong acids go with the strong electrolytes. Our weak acids are going to go with our weak electrolytes. Also, what you will notice is that we are going to have strong bases in this group as well. Strong bases are historically our group 1 and 2 hydroxides and occasionally an oxide. So if you see an OH group, there's a good likelihood of it being a strong electrolyte. For weak electrolyte bases, you will see an example here for our ammonia. This is going to be a weak base, and you will see that when we get to our acid-base neutralization lecture later in this chapter. The most important strong acids do come in on our ionic compounds. The reason why we need to know this is that you are going to use your solubility rules. The solubility rules are going to give you guidance as to how our ionic compounds prefer to break up. If they break up, they will break up completely and be a strong electrolyte. If they don't, they will precipitate and not be in our solution. So now let's go ahead and look at our non-electrolytes. First off, you see in here you have urea. Typically, biologic compounds would prefer to be in solution, but they will not dissociate. The next group that you're going to see here are our alcohols. Alcohols will dissociate. Alcohols will dissolve, but they won't dissociate. As we start getting more and more carbon involved in the chain, the less and less it would like to dissolve in our solution. Finally, as you see with this last group here, these are going to be our sugars, and sugars very much like to dissolve, but they do not dissociate. They stay as the full sugar chain. So let's take a look at an example from the fall of 2017 exam. Which of the following compounds are considered strong electrolytes? So let's look at the first one. We have CH3OH. Now, some people will look at this OH and immediately say that's got to be a strong base. But in all reality, this is an alcohol. This is actually methanol. So our alcohols are deemed to be non-electrolytes. So number one is not going to be a strong electrolyte. If we look at answer possibility number two, this is calcium chloride. This is an ionic compound, and as you're about to see with our solubility rules, it will completely dissociate, so it will be considered a strong electrolyte. As we go to answer possibility number three, this is potassium cyanide. This is also an ionic compound, and it is going to fully dissociate. So right now we have answers 2 and 3 being possibilities. Let's go ahead and look at answer possibility number 4. I have C4H10. This is actually butane and is a hydrocarbon you're going to see in organic chemistry. As you saw on the list that we had before, this has the best likelihood of being a non-electrolyte because it doesn't fall into any of the other categories of being an acid, a base, or an ionic compound. So therefore, answer 4 would not be a correct answer as well. As we look at our answer choices here, that means that our correct answer is going to be answer D. When you're looking for electrolytes, you need to first identify the compound and then figure out what category it is going to be in. So now let us go and look at the precipitation reaction and the solubility rules. So as you saw in the previous video, the precipitation reaction, the whole goal is to create an insoluble solid that separates itself from the solution. So the example we saw before is taking lead nitrate, mixing it with sodium iodide, and then forming our precipitate, which is going to be lead iodide. You see that here in this picture is that I am putting in the sodium iodide. I am going to get a yellow precipitant that is coming out of the solution. So we can write it as the molecular equation, but our better benefit in this case is breaking it up into ions. If it says that it is AQ, this means that it is an aqueous solute and we want to dissociate it. So you will notice that I have taken my lead nitrate and turned it into lead 2+ and 2 nitrate 1 minuses. If it says it's AQ, you are allowed to separate it into ions. Well, how do I know what to do? That is where the solubility rules will come in here in a moment. So as you can see here, I am able to do the same with my sodium iodide. But now look, when it comes to my lead iodide, it has stayed the same because we have the solid nomenclature afterwards to tell us that our precipitant has formed and does not want to be in an aqueous environment. If it says S, we must leave it as is. So once again, as you see here with our sodium nitrate, we have dissociated them as well. When we dissociate our species, we call this the ionic equation. We are creating ions. But the problem with this is, as it was originally highlighted in the previous video, some species don't do work for us. They are known as spectators. They were brought into the reaction, normally by a reacting partner, but they actually don't do any chemistry. So as you'll notice, we have our sodiums and our nitrates are able to be canceled out. These are because they are spectators that don't do any active chemistry in the precipitation reaction. So now you can see we can get a much more streamlined form of an equation. We call this the net ionic equation. This is due to our sodium and our nitrate being removed as spectators. In the net ionic equation, we are getting to the point of the story, and that is what ions are going and forming my solid. We are going to use the solubility rules in order to determine this. So let's take a nice little ionic view of the precipitation reaction that we just saw with one little slight change. So this is right as my compounds are being put in solution. So you will notice that my lead and my nitrate have split. They were originally together as a solid compound before, but when we put them into solution, they broke up into the lead 2+ ion and my nitrate 1- polyatomic. Also, you will see that we have potassium and iodide. So now what we have is two positively charged cations, meow, and two negatively charged anions. The interesting part now becomes is that the lead and iodine are now going to be attracted to each other and are going to form a new solid compound. So as they start to conglomerate and start to interact, this is how they form a solid. You will notice that the potassium and the nitrate don't do this. They prefer to be in the aqueous environment. So now you can see a global view of what happens, and that we will get this to happen for grams on grams and moles on moles of this compound, and this is how we get a noticeable yellow precipitate. So on the left side, you're seeing it in the microscopic view, while on the right side is what you would see in the lab. This is all due to our ions starting to conglomerate and interact because they don't want to be in solution any longer. Here are the solubility rules. The definition of solubility is that it is the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. For this list, it may seem overwhelming and a little bit scary, but I will tell you that these rules are incredibly straightforward, with some exceptions that I will have no problems explaining. The first group that we want to talk about is any ionic compound that contains an alkali metal, lithium, sodium, potassium, rubidium, and cesium, or the ammonium polyatomic, is always going to be soluble. So you can have lithium in any polyatomic, it's going to be soluble. You could have sodium in any polyatomic, it is going to be soluble. So it's really nice that when you see an alkali metal salt or an ammonium metal salt, then you have the ability to know that it is going to be a soluble compound. Now let's go look at the polyatomic anions that are always soluble. That is the nitrates, the acetates, bicarbonates, chlorates, and perchlorates. So in this case, if you have any of those species, it does not matter what metal you mix it with, whether it's lead, nickel, iron, or any of the exotic ones, because if in this case it is bound to one of these anions, it will be soluble in solution. This is a very nice way of getting toxic metals into solution, and you have seen the health ramifications of that. Now let's go to a group that's a little bit more difficult. That is the halides. The halides of chloride, bromide, and iodide are historically soluble except for 3 exceptions. Those are silver, mercury, and lead. In the last slide, you saw that we were using lead iodide. This is how we got that precipitant, is using this rule. You would look and say iodines are historically normally soluble, but lead falls under one of those exceptions. So you want to check the rule on the left and make sure there are no exceptions on the right. Sulfates are also historically usually soluble, except for 6 exceptions. the three that we had before when dealing with our silver, our mercury, and our lead, but now you will also see three of the alkaline earth metal cations. Meow. So in the case of a species such as calcium sulfate, this is going to be insoluble because we have one of the ions that makes this an insoluble exception. So remember the rule on the left, but you may have to apply one of the exceptions on the right. So now let's go look at the historically insoluble compounds. Those are going to pertain to some of our polyatomic anions. Those are carbonates, phosphates, chromates, and sulfides. So now if we have metals that are bound to that species, we will typically have an insoluble compound. Except, and now let's go look at this rule, compounds containing alkali metal ions or the ammonium ion. So our soluble exception here is actually just a reiteration of rule 1 here at the top. So this is going to give us a little bit of our versatility. So if we were to have a compound such as potassium carbonate, everybody will sit there and say, but carbonates are going to be insoluble. I agree, they are historically supposed to be insoluble, but the rule that actually is going to apply is the potassium, and that falls in under the solubility rules of being soluble. So this is actually how we can get some insoluble ionic partners into solution, is partner them with one of our alkali metals. Another group that is historically insoluble are the hydroxides, except for those of the alkali metals and the barium ion. So if we were to have such things as potassium hydroxide will be soluble, sodium hydroxide, which is going to be nice because this is a strong base we use in the lab, and another one that we might end up using from time to time is barium hydroxide as well. Now, these rules don't cover every possibility, and we will use some understanding about what we combine in what other parts, but for the most part, this will give you a really nice guide of about 90% of the compounds that you are going to see in your general chemistry. So let's look at some examples of the precipitation reactions. So here we have our first one, which gets a very nice vibrant orange color, and that is going to be cadmium sulfide. Remember from our group that sulfides are historically insoluble, and cadmium is not an alkali metal or not ammonium. Therefore, we know we're going to form a solid. You see it here. Well, this is also true for our lead sulfide, and you'll notice that this turns into a very dark, almost black color. Now let's go look at our third example, and you will see that I get nickel hydroxide. So remember that our hydroxides are historically insoluble, except for those of our alkali metals, potassium, sodium, lithium, cesium, or that of barium. Nickel is not one of those. So this is how we actually form this nice, vibrant green precipitate. Also, when we're talking about our hydroxides, you will now see aluminum. Notice when it comes to aluminum, does not fall in that group, and that is why you form this very nice white wispy precipitate. Now, the reason I show these precipitates is that these are actually sometimes more the exception than the rule. Not in that they don't follow the solubility rules, it's that they actually produce a color or a characteristic property. Most of the precipitates that you are going to deal with in our course are going to be white solids. So it's going to be very difficult to identify something just based off of the color and its properties. It's best to theoretically understand the solubility rules and be able to predict what solids you're going to form. So how do we do that? Well, we can solve net ionic equations. So let's look at this example. I have silver nitrate and potassium sulfate. So the question will become, what should I form? Well, our positively charged cation, meow, of one species should go and react with the anion of the other. So one thing I should go and do is get silver Remember, this has a 1 plus charge, so I need to have a 2, and I would go and get sulfate. The other species that I should end up getting in here is going to be the other positively charged cation, meow, going and reacting with the other anion. We're doing an anion switch. So this means that I should end up getting potassium nitrate. So now you're probably first noticing that this is not balanced currently. So what I would need to do is go and put a 2 in front of my silver nitrate, and that is going to give me 2 potassium nitrates there. So now this is balanced atom for atom based off of the rules that we've seen previously. But now we have to look at the solubility rules. Remember that if I have potassium or nitrate, it is going to be soluble. So the fact that I have both of them is meaning that this is going to stay in solution. Now let's go ahead and look at our silver sulfate. Sulfates are usually soluble except for those of silver, mercury, lead, calcium, strontium, and barium. Because of the silver, this is now going to precipitate. So now what I have done is written my molecular equation. The next thing I need to do is write my ionic equation. So what I need to do is follow the solubility rules and break up every species that I am allowed to. So as you can see here, I have gone and broken down my silver nitrate into silver 1 plus, nitrate 1 minus, and you can also see I've done the same thing for my potassium sulfate. But I must leave my silver sulfate combined. Remember that if it says it is solid, it must stay intact. When it comes to my potassium nitrate, remember that if it has a nitrate, it is going to dissociate, and I will split those species up. So if I were to go and balance this very quickly through here, you will see that I am now able to go and cross out species that I know are going to be spectators. So now that is going to be rule 3. I am going to cancel out the spectators that I had before. So now what will happen is that my nitrate and my potassiums are going to leave. I will keep my silver sulfate once again as a solid, but now my potassiums that I had prior are going to be canceled because of the 2 potassiums on the left side, as well as my 2 nitrates that I had before. So this is now going to take my ionic equation and get rid of my spectators. So the last thing I have to do is just check the charges and the number of atoms are balanced in my net ionic equation. So in this case, I know that I need to have 2 of my silvers in order to have my silver sulfate compound that you see here. This is the process that we would expect for you to take part in as you are going and working through your precipitation reactions. Let's try some examples. The first thing I want to do is see if you can identify some soluble and insoluble compounds. So let's first look at A, which is potassium sulfate. So if we were to look at our solubility rules, you will see that this is going to be a soluble compound. The reason why, and in most cases, a lot of students will say, this is due to the sulfate. That is not the case. It contains potassium, which is an alkali metal, and this will make all compounds soluble. So if you see potassium in a salt, it is going to be soluble. So let's go ahead and look at B. You can now see that we have sodium chromate. So as you would look at your list, some of you would notice that chromate is going to be an insoluble compound. However, notice that the cation, meow, that we have is sodium. This is an alkali metal, therefore this is going to be soluble as well. So we took a historically insoluble anion and made it soluble as a compound because of the sodium. So let's look at C. We now have lead 2 hydroxide. So remember, for our hydroxides, these are usually insoluble, except for those of the alkali metals and barium. Lead is not one of those. So this will follow the rules, and you are now going to get an insoluble compound from our species. So as you can see here, the solubility rules are very easy and straightforward to follow. So now let's take a look at this example. When dealing with the solubility rules, which of the following compounds are considered soluble? This is a question from the fall of 2018 exam. So let's look at our first example, and you will see that I have calcium sulfate. So as you saw before, sulfates are historically soluble, but calcium is one of those alkaline earth metal exceptions. Remember, for sulfates, it is silver, mercury, lead, calcium, strontium, and barium. This makes number 1 insoluble. Well, now we can go to number 2, and you will see that I am going to have iron 2 chlorate. Well, chlorates are always going to be soluble. We do not have to worry about our iron. 2 is going to be soluble because of our chlorates. So let's go ahead and look at answer 3, and you will see that I have a phosphate. But like the examples that we saw before, I'm not worried about the phosphate, which can historically be insoluble, because I am focusing in here on the sodium. The sodium is always going to make our phosphate soluble in this case, because all sodium compounds are soluble. So number 3 is a possible answer. Let's look at our fourth answer. We have chromium hydroxide. Hydroxides are historically insoluble, except for those of the alkali metals and that of barium. Chromium does not fall into that group. So we know that answer 4 is going to be insoluble as well. So as we look at our answer choices, we need to find one that contains answers 2 and 3, and you will notice that that is going to be answer C. This is how you should look at problems when dealing with our solubility rules. For our last example in this idea, let's talk a little bit about building our net ionic equations, because you're going to see in our last example of the day just how important that is going to be. So now what I need to do is predict to see if I will get a precipitate between potassium phosphate and calcium nitrate. So what I need to do is write the net ionic equation below. So let us go and start with what we know we have. So we have potassium phosphate. Well, we know that this is going to be soluble because it contains potassium. Then we are going to mix that with our calcium nitrate. And remember that all nitrates are soluble as well, so we are going to say that that is aqueous. So what we need to do is go and do our ion exchange. So this means that we are going to end up getting potassium and nitrate to now mix. Is this soluble? And I will tell you with great certainty that because of the potassium and the nitrate both, this is going to be a very soluble compound. Then finally, what is my other compound that I'm going to form? Well, my calcium is 2 plus, my phosphate is 3 minus, so what we will end up getting is Ca3PO4 2. So now you can see that we have to do a little bit of work here to balance our equation. So we will get 3 of my calcium nitrates. I am going to need 2 of my potassium phosphates. That will give me 6 of my potassium nitrates, and I have a balanced chemical equation. But now we have to think of the solubility rules. Phosphates are usually insoluble, except for those of the alkali metals and ammonia. Calcium is not one of those. This is going to form a solid, and that is the white solid you see in the picture. So now what we need to do is write the net ionic equation. This means that I have to cancel out all spectators. Well, the spectators in this case are going to be my potassiums and my nitrates. So now what I am able to do is write an answer of 3 Ca2 pluses in solution, so that would be aqueous, plus 2 phosphates, so we'll have 2 PO4, 3 minuses, going and forming our Ca3 PO4 2 solid. What I have now written at the bottom is the net ionic equation. For most net ionic equations, I want you to get very familiar with writing the cation, meow, out front first, then followed by the anion to form the solid compound. This is just a historical way of doing it. However, it does not make it entirely wrong if you were to go and write the two combination the other way. So let's look at this final example, and you will see the importance of the last example that we did. This was from the fall of 2017 exam. Which equation is the net ionic equation for the aqueous reaction of nickel nitrate and sodium carbonate? Well, what you want to see first is that for answer A, I've actually gone and written the molecular equation. You will see that I have my nickel nitrate, but the nice part about it is that we know that all nitrates are soluble. So as you can see with this nitrate here and the sodium nitrate in the product, I am able to cancel out the nitrate because we know it will be a spectator. So let's look at our other species. Well, we will have sodium carbonate. We know that that is going to be soluble because of the sodium. So we have our sodium on the reactant and the sodium in the product, and that will cancel as a spectator as well. So now you will see that I am left with nickel carbonate going to form nickel carbonate solid. So this is the answer that I should look for, and you will notice that that answer is seen here in answer D. I have my nickel 2 plus cation, meow, and my carbonate, and I will go and form the solid that is going to be insoluble based off of the solubility rules. If you look at answers B and C, you will see that I'm dealing with nitrate compounds. That means that I'm trying to build a net ionic equation using a soluble compound. That cannot be the case. So answers B and C are not going to be correct, and neither will be E. There's a lot of people that are going to answer letter A, but that is the molecular equation. I want the net ionic. So in this case, I can get rid of answer A. In this video, you saw how important it was to know not only how electrolytes behave, but then the precipitation reaction that uses the solubility rule and how we are able to predict the products that we are going to get in a reaction and see what our precipitates are going to be. We are going to use this in the next video as well as future videos to show you how we can calculate the mass of those solids. Have a great day.